Okay, and it looks like audio is working. Great, let's get started. Thanks everybody for attending. My name is Kevin Gleason. I work here on the StableHLO team at Google, and today we're here to talk about getting StableHLO from PyTorch, JAX, TensorFlow, wherever you want to get it from, and eventually quantizing it. We have Jen and Xing here to talk about that as well. So yeah, agenda for today is basically this flowchart. There's a bunch of popular frameworks, and we want you to be able to get StableHLO from those frameworks and into the target format that you want them to be in. Maybe it's StableHLO, maybe it's quantized StableHLO, or maybe it's a JAX model that you quantize and then put in the save model to serve it somewhere else. The point of this whole talk is I want to show off some of the APIs we have today to do all of these conversions and to make this ecosystem of getting StableHLO and converting it as simple as possible. So also feel free to hack along. Everything I'm going to be presenting today is a public tutorial. I'm even going to go there myself. It's on the StableHLO repo. So we go to StableHLO, find it, open it, and then under docs and tutorials. There are 3 now. There are more coming. This is sort of where we're going to house this sort of thing, the pieces of StableHLO that we're trying to make easy and things that you shouldn't have to think about. So we will open and collab. So to get started, let's talk about extracting StableHLO from JAX. Font size looks okay, I think. All right, so the first step of getting StableHLO from JAX is obviously installing the dependencies. Here we're going to use JAX and then JAXlib. JAXlib is where the XLA and StableHLO side of JAX is packaged. And then we're also going to use Flax and transformers just so that we can deal with exporting a real model from the wild, not some simple toy example. I've already run this step, but feel free to run it locally. For starters, there's one little bit that I'm hiding, and it has 0 functional purpose. This uses some internal stuff, so I keep it hidden. But the only purpose of it is to pretty print the StableHLO so that this can read more like documentation. It does nothing functionally beyond that. It's just for easy readability. Everything else is better supported and doesn't use internal APIs. All right, so exporting a model from JAX. This is where we use the JAX export API. Under the hood, this export API uses jax.jit. This is the process. JIT is the process where JAX takes a Python program, traces through it, and constructs what it calls its internal IR, which is called JAXPR. And then there is easy mappings from JAXPRs to StableHLO, and that's sort of how the process of going from JAX to StableHLO works. So as a rule of thumb, a function must be JITable to be exported to StableHLO. So let's start with a super basic JAX model. This is going to be a plus function. We're going to use the JAX numpy API for add, takes 2 arguments, x and y, and we're going to also use this jax.export API that I was talking about. So looking down here, let's say for this example, we'll use 2 input arguments that are both int32s. One thing to note about the export API is that it uses more abstract shapes to trace. So not the concrete input argument of tensor with the value 1, but it wants to know that it's a 1-dimensional tensor of type int32. And so to do that conversion, you use this shape dtype struct thing, and the numpy values know their data types and know their shapes, so it's super simple to construct this more abstract representation. Now we can use that jax.export. We pass it our function, and then we tell it what input arguments to use to trace it, and out comes just a great .mlir module. And when we pretty print it, you can see StableHLO.add. We've successfully extracted our StableHLO program. Let's say you wanted to do some other things, subtract 1. Super easy to get StableHLO from JAX. All right, now let's talk about a more real-world model. We're going to use ResNet 18 here from the Hugging Face Transformers repo. The majority of this section I just copied directly from their documentation. So let's construct a ResNet model from a JAX Hugging Face transformer. We import it. This is all copy pasted from that doc page I just pulled up. And we can make it pre-trained and return dict equals false. Again, straight out of the documentation. And it also had sample inputs in the doc. and we know exactly how to go from our concrete sample input to a more abstract shape. You pass it into the D type with the shape and the data type. And now this is again exactly the same as our simple model from before. You have export. First argument is a callable. In this case, it's a model, not a function. And then you pass it the shapes that you want to use to trace it. And when we run this one, out comes our more real-world ResNet 18 model from JAX. You can see that I truncated it because it's a bit longer, but it has the main function, some large constants that are elided for the sake of pretty printing this. And then at some point, I guess that a ReLU was used, and that showed up in the StableHLO log as well. So again, larger model, real world, super trivial to get StableHLO from a JAX program. Next, we'll talk about dynamic batch size. So a super common use case is you want to defer specifying what the shape of a certain tensor is until maybe compile time, maybe even later than that. But you want some way to say, I need a tensor and this first value is a question mark, or one of the values is a question mark. I'll tell you what it is later. The way that JAX accomplishes this is using symbolic shapes. Let's even look down at the example here. A symbolic shape in this case is A. In the first example, we had this 1/3, and in this one, we have an A/3. The way that symbolic shapes work is A represents some unknown value, and you put that unknown value in a symbolic scope, and all uses of A in that symbolic scope refer to the same value. So if you were trying to do a dynamic matrix multiplication, you just need to make sure that the A's line up in the same spot such that it can be verified that it's a valid matrix multiplication. So in this case, we will make a symbolic scope for those values like A to live, and then the same API from earlier to make our abstract shape. Instead of passing it any kind of a concrete numpy shape, we use the symbolic shape function here and say, all right, the shape of this one is A/3 by 224. And now when we run that one and export it, it's the same export API, the same callable. The only thing that's changed in this case is that the argument shape is now a dynamic shape with a symbolic value A. And out comes exactly what we wanted, a tensor where the first value is an unbounded dynamic dimension. And if you look through the rest of the program, you can see that there's some slightly different code generation, because when we don't know the value of A, we need to do broadcasting on the fly. Whatever the value of A turned out to be, we need to dynamically make sure we broadcast to that value of A. And so JAX takes care of all of that code generation in StableHLO for you, as long as you provide the right input shapes. And then inversely, if you know the static input shapes, we have APIs. It's trivial to take a dynamic program and refine it back into a static program. Okay, and then I guess last for JAX, let's talk about exporting to saved model. This is a more common use case if you have input pipelines that already use saved model. So there's or tooling as well. There's things like TensorBoard, there's TensorFlow serving is a popular way to serve models. But if save model is on the critical path, we have APIs for that as well. In this case, it is called JAX to TF. And it uses the JAX export API under the hood that we were just using. And so a lot of the arguments you're going to see are the same. We import JAX to TF and call convert, pass it our ResNet 18 model, and then here's the same polymorphic shape string from the previous example. And then that takes care of packaging it all, and now it's ready to be put on a TensorFlow module. So how do we make a save model? You have to, save models are a TensorFlow thing. So import TensorFlow, you create a model, and then assign a function to it. And here's the thing that got exported from JAX. The only other bit of bookkeeping that needs to be done is you have to use the TensorFlow shape of that program's input arguments. So we had that unbounded dynamic value, and then the rest of them were static values. Nothing too fancy, fairly self-explanatory, I suppose. But when we run that one, that packages it. We have a save model.save that takes that model, puts it in the directory, and you can see that we have the save model protobuf. There's some variables, some additional metadata in there. And what can we do from here? There's APIs as well in TensorFlow to just load from an arbitrary save model and run, evaluate it, call it. You can, given that this was a dynamic model that we packaged, you could actually use sample inputs of any shape that was compatible with the dynamic program that we compiled. So you can specify your batch size, it takes care of refining it, compiling it to XLA in this case. But yeah, super simple. A few bits of common troubleshooting for JAX. As I mentioned, if you can JIT it, it can be exported. So the first step is try to get jax.jit to work. One example was somebody was asking about AlphaFold, and in the middle of, at the top level of the AlphaFold model, there's a jax.jit. So right away, you know that you can export the AlphaFold apply model pretty trivially using exactly what we've learned here. Then yeah, beyond that, there's some common troubleshooting steps for JAX there. I won't spend too much time there. And that's it for JAX. Next, let's talk about going from PyTorch to StableHLO. So again, this is all on the StableHLO repo. Their docs, tutorials, and here's our PyTorch example. And anytime you want to run it yourself or tweak it, you click open in Colab, and here we are. All right, so PyTorch, the bridge from PyTorch to StableHLO is called PyTorch XLA, and they have some very nice APIs in this torchxla.stablehlo module. Here's their documentation on it, but we'll be walking through it here, so no need to look too close at it. For this example, we're going to use Torch Vision to get the ResNet 18 model, and then Torch XLA to export that model to StableHLO. PyTorch and PyTorch XLA was nice enough to cut a release the night before a tutorial, so had a good old heart attack this morning to make sure this all still worked. Good news is that it did. All right, step one, exporting a model to an FX graph. So the way that this is structured, and I guess the way that the JAX one was structured as well, is you build your model and then you export it. Two completely separate, not intertwined steps. And in this case, building your model is entirely PyTorch. So you can see in step one here, it's all Torch, Torch Vision, and Torch Export. So StableHLO or PyTorch XLA has yet to enter the picture. What we do is we import our Torch Vision and create a ResNet 18 model, provide it some sample inputs, and then use the basic vanilla PyTorch export API, which takes in a model and then some sample inputs used to trace it. And so now what we have here is a FX graph in an exported module, in an exported artifact here. And now this is where PyTorch XLA can enter the picture. We use this Torch XLA StableHLO module, which has a function that says, if you have an exported PyTorch artifact, we know how to convert that into StableHLO. And so we call that and pass in this thing that was exported from the previous step. And out should come our ResNet 18. Now, for dynamic batch dimensions for PyTorch, this is a feature that we spent a whole lot of time working on in the first quarter of this year. So it's a relatively new feature, but we have it working on a whole bunch of production models now. But the only reason I'm saying this is this will be included in the 2.4 public release of PyTorch. If you wanted to use it today, it's in the PyTorch XLA nightly. But given that given that we plan to use this documentation and test it in CI, we decided it's probably best to not depend on nightly releases to avoid digging through issues that should not be our problem. Okay, so how does it look like to export something with a dynamic batch dimension from PyTorch? It's exactly the same as it was before. There's the PyTorch world and the not PyTorch. There's the PyTorch world and the PyTorch XLA side. So dynamic batch dimensions and tracing that through a program happens entirely in the PyTorch world. So there's this API where you specify a dim, and it has a name. I'm guessing this is just a symbolic name similar to the A in JAX. And then you can add constraints to your dimension. In this case, we're just going to say that this batch dimension's max value is 15. And then Torch uses this to generate some dynamo guards to make sure that your value is actually what you said that it would be. Create some dynamic shapes, and then call the Torch export API, the exact same two arguments from before, but now you also specify that the zero dimension of the batch the zero argument is zero dimension is an unbounded dynamic value. It's something that we will refine at a later point. And now all of that information, the FX graph, the sample inputs that were used to trace, as well as the dynamo guards, the dynamic shape information, is all contained in the PyTorch exported artifact. And that means that our API call looks exactly the same. Export program to StableHLO. And when you print that one out, this is how you would get your unbounded This is how you would get your ResNet that uses a question mark in the first dimension of the input argument. And again, this all works in the PyTorch nightly branch, or the Torch XLA nightly branch. So feel free to try that out if this is a use case that you're trying to get working in the near future. A couple other APIs to show off from Torch XLA is that you can take your StableHLO exported program and save it to disk and reload it. StableHLO program.save, specify a place to put it, and then as well as you can reload it and then call it. This is not using saved model. This is just dumping the raw StableHLO bytecode. This has full forward and backward compatibility to it, as well as some additional metadata on what the argument shapes, input argument shapes and sizes are. And then the last one here is just a debug dump. I don't think that the forward MLIR actually does anything because the bytecode is the stable thing that gets reloaded. But if you wanted to take a look at the StableHLO and have it easier to visualize, that's what the forward MLIR there is for.
So is the stability guarantee only provided for the bytecode?
Yes.
Oh.
Yeah, so it's MLIR bytecode though. So any MLIR APIs, like just the typical ir.parse, works fine with that bytecode.
But the textual form might change.
Textual form might change, exactly. Yeah, right. There's yeah, another benefit of that is like if you were doing things like adding operands or adding attributes or things like that, that's far more difficult to manage at the textual level. Where when you're dealing with just bytecode and constructing the actual raw C++ stuff, it's the APIs for it make it a whole lot easier. Okay, and then the last step here is export to saved model. Again, easy to do it from JAX, similarly easy to do it from PyTorch. I won't go through running this one for the sake of time, but there's a nice function called SaveTorch module as TF-save model. And you pass in your ResNet, you pass in your sample input and a place to put the save model. Under the hood, this uses Torch export with the sample inputs. There's also an input argument if you want to specify those dynamic shape constraints. And then that will output your save model, which similarly, identically to the JAX example, you can load and execute. One important thing to note is once you have your save model, there's no dependency on PyTorch, JAX, anything else. You just need a way to read the save model, TensorFlow, and a way to compile it, XLA, which is packaged in TensorFlow. Why is a load argument a directory instead of just a bytecode file path? Yes. Mostly due to the structure of, this is a saved model, and the structure of a saved model is, here's the directory output. It's a protobuf with the saved model in it, and with a StableHLO serialized as a bytecode blob in it as well as some additional variables and metadata. So the reason it's a directory is just because that's how save models are structured. They're not a single file, they're a collection of files. Okay, and then common troubleshooting. The most common issue when dealing in PyTorch is dependencies getting out of sync. Like PyTorch XLA, PyTorch, Torch Vision, they're all very intertwined with each other. Anytime one of them cuts a release, all of the other ones cut a release on the same day, and that's what happened yesterday. So just make sure that all of your dependencies are on the same correct matching version. And then otherwise, it's, as we've shown in this example, there's a PyTorch part, which if you have issues on that with Torch export, should be resolved in upstream PyTorch with tickets. And then there's a Torch XLA part, if you have issues on the bridge part, a ticket on the PyTorch XLA repo. And both of these teams are very good at responding to tickets. So the better that you can give a example, like if you had something like this collab to show off the issue that you're hitting, the quicker the issue tends to get resolved. Okay, and then last is TensorFlow. This one I'm going to do, we just submitted the nicer Python APIs, so I'm just going to show this off and not run it. We're waiting for it to get into the TensorFlow nightly pip wheel. Unfortunately, we got them submitted like 2 days ago, I think, and it has not yet made it to the public pip wheel. So we'll just look over this one. But all these APIs exist. If you wanted to build TensorFlow yourself, you could run them today. I don't have that expectation. But the TensorFlow example here is simple add one model. Just as a Keras model, it adds one to itself. And then we create our saved model. Only purpose of this section is to get a saved model to demonstrate for TensorFlow. I think I actually asked Gemini to generate this code for me and then just copy pasted it here and we got a saved model. So looks like it worked. Here's the new API that we're working on. Just plain and simple, TensorFlow to StableHLO. We want it to be as easy to use as the other ones. It should be trivial to come from any framework or to go to any format. And in this case, it's this TensorFlow to StableHLO, which we imported as TF to StableHLO. And when you have that save model path, again, using a directory because it's a collection of files, you can just call TF to StableHLO, save model to StableHLO, pass your path. You get back some MLIR bytecode. Again, working on this API, we can make it just return the module directly, but we figured it's simple enough to just call IR module parse on the bytecode that comes back. But yeah, that's how you would extract things from TensorFlow. One other note, also one other thing to note is that this will work for any of the save models exported from JAX, PyTorch, or just an existing TensorFlow save model that you find in the wild. The only caveat for TensorFlow created save models that you find in the wild is like today's use cases that we've had for TensorFlow don't have unbounded dynamic shapes, or by the time, or we leave them in TensorFlow world until we know the concrete shapes because we're about to compile it. And so the unbounded dynamic shape support for TensorFlow to StableHLO is a bit more limited. So there are cases where you do need to specify concrete argument shapes for this API to work in the near term. If that's a use case, then we would, if that's a more higher priority use case, we love to hear it. But it seems like the use of TensorFlow seems to be going down, and likewise, we should support it as much as it's needed. All right. And then, yeah, ongoing work. Basically, make it easy. We were showing off how easy it is to go from all these places to StableHLO and to go to save model. We'll hear about the quantizer next, but we're looking into better TensorFlow APIs. We actually do have another tutorial that I'm not going to go through, where if you have an arbitrary blob of StableHLO and you want to package it in a save model, that's easy as well. And then lastly is maybe some better XLA APIs. Maybe it's HLO that you wanted to take a look at, but you have a StableHLO blob. We could make this super easy to go between the two of those. Maybe even other APIs in XLA if those are of interest as well. The bottom line here is we're looking for feedback. We're interested in what everybody wants to do with XLA and StableHLO, and we can design APIs accordingly. And with that, I will pass it off to hear about the StableHLO quantizer.
Hi, I am Xing, and me and my teammate Jen will be presenting the StableHLO quantizer today. And if you attend the OpenXLA weekly meeting a few weeks ago, you may already heard from Jason from our team about StableHLO quantizer. And today we are talk about more details about it. So first question, why quantization is hard for ML developers? There are multiple reasons. The first is there are a lot of existing frameworks and hardware, and more hardware, framework and hardwares are emerging. So it's very hard to build a quantization solution for each of these stack. For example, building a quantization solution for PyTorch for GPU and building quantization for PyTorch on TPU requires totally different tech stack. The second is quantization is a lossy transformation. It inevitably will decrease the accuracy of the model, and finding the optimal configuration is very hard. Also, the third reason is quantization itself. The concept might sound easy, but there are a lot of details of implementing. Like I said, you have to know a lot of detail about the framework and the target hardware to actually implementing the quantization. So we decide to build our universal quantizer that are framework and hardware agnostic with the offering that StableHLO provide. It's natural to decide we build the quantizer at the StableHLO level. Here is the graph of the positioning of the StableHLO quantizer. You can see that it can used for all the TensorFlow, JAX, PyTorch, and the quantized model that can be consumed by different compiler, including XLA, TF-like, and applied to whatever hardware you want to run. So let's look into more detail about the component of StableHLO quantizer. On the left side, Kevin already covered that and how to export Jack's PyTorch TensorFlow model to save the model. And you only need to prepare an quantization config, which is a proto, specify the quantization recipe, and feed the config and save the model to StableHLO quantizer. It will go through the pre-calibration, basically the preparation for the calibration, then the calibration, which is running the model on a real runtime to collect the stats of the tensor, and then the post-calibration, which do the real quantization and the cleanup. And after that, StableHLO quantizer will export quantize the saved model, and you can deploy it on the hardware you are interested in that can either support a uniform quantized type, or if it doesn't, it can export the int op that can run on your hardware. So I will talk into detail about each component here. And a summary of our current results is we applied the StableHLO quantizer on 60+ models in production, and with 2/3 of success rate, and have 20% plus mean performance improvement. Okay, so let's look into the detail of how we do the graph transformation to accomplish the quantization. So here are the MLIR graph of simply just StableHLO.general. And please only focus on the ops that been highlighted, because it's very hard to look through all the graph. So here is the StableHLO module that we exported from a TF or JAX here, and it only has a StableHLO.general. And the first thing we do is to identify the ops that we want to do quantization. For this example, is the .general itself. So we wrap this function into a composite .general function. And also we use in the main function, there's a TF-XLA call module, which basically wrap this function. And the next step is before and after the TF-XLA call module up, we insert a TF custom aggregator before and after. So basically, you can imagine that TF custom aggregator is a counter. It will count the data going through it and record the min max value of it. So you can see now all the min max are 0 because it's just initiated. Okay, now we're going through the calibration. So we actually serialize the model and run it using the calibration data in the runtime. And the TF custom aggregator will record the stats during the calibration. So now we can see that the TF custom aggregator now has the min max value in it. Next step is we just convert the TF custom aggregator into quantfork stats. They are basically equivalent. So here we have the data stored in the bytecode here. The next step is actually we translate the stats into our quantfork QCast and quantfork DCast. So quantfork, you can consider QCast and DCast is generally the quantization op and dequantization op. So here we can see now we have quantization op both before and after the XLA call module op. The next step would be we combine the dequantization before the float op and the float op, and so we combine the dequantization, the float op, and the quantization op after. So now then this will become the op we want to quantize, and after that we only have quantization op before the XLA call module op, and only the dequantization op after the XLA call module op. And next, we just convert the quant fork QCast and DCast into StableHLO uniform quantize and StableHLO dequantize. So basically, they are equivalent. The last step would be we look into the previous quantize composite.general function, and we actually apply the quantization parameter to the StableHLO.general. Now you can see that the signature of the .general now become taking the uniform quantize type and output uniform quantize type. So after that, the whole quantization is done. And there are other optimization happen afterwards, but I omit it from this presentation. Okay, I'll hand over question.
Yeah, a couple questions. So there was a bunch of other operations that are not in the StableHLO namespace or the dialect. Is this transformation part of StableHLO? Is picking up dialects from TensorFlow and other places, or how does this work?
Yeah, so we only doing quantization for the op that's supported by StableHLO. Does that answer your question?
Sorry, can you say?
Yeah, we only do the quantization for the op that exists in StableHLO dialect.
Yeah, I'm talking about the.
No, my question was like your graph transformation. It's part of StableHLO repository, right? And it but it's pulling in. There's a bunch of passes you were going through pretty quickly, but I saw some other ops in there that were coming from other namespaces. I was just wondering how those dependencies got pulled in.
Can you repeat your question?
So in the earlier slides, when you're doing the graph transformation walkthrough, there was some tf.xla call or something, and then there was quant fork. Like, where are those coming from? Are they part of StableHLO or something else?
Yeah, I think
that's kind of like general quantization library that we use. So that's like not particular to StableHLO ops, but part of like how we implement quantization driver. Yeah. So.
Can you repeat the mic?
Okay. Oh, sorry for the people in GC. Yeah. So I was just saying that. So as Xing said, we do quantization only for the StableHLO ops, but as you said, quant fork or some other TF custom aggregator or other things, those are just used to, for example, collect the statistics for calibration, collect the statistics to actually get the scales and 0 points, or kind of like do. It was kind of like. Implementation helper kind of things that are not StableHLO. Yeah.
I was going to add, for the sake of dependencies, quantizer is its own project, own repo. And if you think about it as a black box, it's floating point StableHLO in. We're seeing some implementation details here, and it's quantized StableHLO out. So all those things get washed away.
In terms of dependencies, now, is it going to be dependent on TensorFlow because internally you're using TensorFlow to collect statistics and all that?
Just the quantizer, which is its own repo, separate tool.
Okay, not the TensorFlow base. Okay.
So you do mention that there are .general that for different quantize format. So if we're implementing like a backend for StableHLO, that means we'll have to implement all these. And what kind of quantize format are we like doing, and how in general is like the way the quantize like specify block quantization, tensor quantization, like what kind of different quantization schemes are going to be supported, and what format it's going to be?
Yeah, so for now, I think we support static range per tensor and per channel quantization, and we are going to have plan to support more algorithm. Is that anything you are particularly looking for?
Okay, and what about the data type?
Yeah, the data type we are now currently supporting in 8, but are other like in 4 also in our plan.
Right. And we also have like very close to launch implementations for dynamic range quantization and weight only quantization currently in int 8.
Quick question on so you mentioned like it gets around the dot general, but what about like if we do any device specific optimizations and we fuse certain ops, so do we calibrate after it, like how?
Yeah, so I for the calibration part, I think it's the same. The fusion optimization for each hardware are happen after the quantization.
But wouldn't stats be changing in that case?
So that's actually a really great question. And so actually the collab that I'm going to demonstrate right after is going to show more examples of what you said about which things are going to be fused together and then like which patterns will be quantized.
Okay, thanks.
Okay, then I'll hand over to Jane for the demo.
All right, so thank you, Xing, for introduction to StableHLO Quantizer. And all right, so is this, yes. Okay, so now that you know how to export different ML frameworks into StableHLO module, I'm going to be showing you a quick demo on how to quantize the StableHLO graph into quantized StableHLO graph. Yes, so before I start, so most of the codes here are already available in open source GitHub, but some of the things, especially in terms of full-fledged open source packagings, we are yet to make this fully available in packages. So once they're available, we'd like to share this in the OpenXLA repository. And so for today, just please follow along my screens. So, all right. So Kevin just told you how to export your various JAX or PyTorch or TensorFlow models into StableHLO module. So this is where we're going to start actually. So you have something like a ResNet 18, which is going to be converted into StableHLO module with JAX to TF. And it's going to be in save model, which has the StableHLO module serialized in that save model format. So that's where we're going to start. So we're going to quantize that StableHLO module inside the save model, of course, like TensorFlow, then straight as is. So you just saw from Xing's diagram that this is the design for StableHLO quantizer. So it's going to have two inputs mainly. And the first being the save model, which is essentially StableHLO module. And the second being quantization configuration, which has all the recipes on how to quantize the model, whether it be what kind of like static range, dynamic range, etc., and which layers you'd like to quantize and what kind of final quantized types you'd like to get out of this. So based on this quantization recipe, the StableHLO quantizer is going to transform the module and then quantize the graphs. And the final graph, which is quantized StableHLO graph, is going to be served as either as uniform quantized types, which is essentially a type with scales and zero points together, which a lot of your hardwares already do support. Or if your hardwares don't support it, we can also unpack this into separate integers, which is what we currently do for TPUs. So there are options available here. And of course, because StableHLO itself is an intermediate representation that is intended to be hardware agnostic, of course, we support both server usages and ODML usages. So for today, so I'll be demonstrating both the server and ODML usages. And yes, so for server side, it's going to utilize the quantization Python API for StableHLO. And it's going to input the save model, and it's going to output the save model with quantized StableHLO inside it. And for ODML side, we actually integrated the StableHLO quantizer into TF Lite converter. So usually when you run TF Lite converter, you're going to have the option to run the TF Lite quantizer. But with this, you now also have the option to run this with StableHLO quantizer. So let me walk you through the APIs. So this is what it looks like for the server side. So you can see that this is what we previously mentioned in the design diagrams of quantization configuration. So this has all the information on how to quantize the model, including which methods or which layers or which types or anything like that. And of course, yeah, for static range quantization, it would have the representative data set that you also mentioned earlier. Yeah, so that would be the quantization configuration, and we would be feeding this into the Python API quantization.quantizesave model. So the very first input here is going to be what you have from Kevin's demonstration. So that's going to be the path that contains the exported save model. And you're going to also provide where you want your quantized save model to be at. And you're also going to provide your quantization configuration, which has all the information. And that's going to output the quantized save model. So let me actually walk you through this with the graph transformations. So prior to quantization, your StableHLO module would probably look something like this. So you have all of your float constants like this, and your float ops like this. And one thing to note is that StableHLO, because it's intended to be supported for various hardwares, it's very granular and primitive because we want to support all hardwares. And of course, some different kernels may have the design choice to either make this a fused kernel or not. But of course, because StableHLO wants to be universal for hardwares, that is the design choice we took. But for quantization, we actually want these to be fused together because that's beneficial for usually for accuracy and performance. So you mentioned earlier about why how we kind of like have the scope of like which things we'd like to fuse together. So usually for our case, so for general multiplication ops such as convolution or dense ops, they have adjacent bias add and activation clipping, which often come together and are much beneficial for quantization if we just treat it as a one pattern. So what we do is we actually lift these, for example, like this thing would be just like convolution with adjacent bias and activation clipping, and we want to treat this as one quantization pattern. So we would lift this, and then we would lift this as a function, and then quantize it. So this is how it's going to look like in the quantizer after the quantization part. So you can see that for the constants, it's going to have uniform quantized types like this, and this is the main graph. And you can see that the previous different convolution, maximum add, etc., are now combined together into separate functions. So the main function is going to call the lifted quantized function. And the quantized function, as you can see separately, are essentially what we previously saw, but also with the quantized data types. And of course, for the purposes of demonstration and letting you understand how we work under the scope, this is separately explicitly shown as functions, but of course, they would be inlined in the main graph so that we don't have the additional overhead. So that's what we look like under the hood with lifting and then quantizing different fuse patterns that are often beneficial for quantization. But if your hardware doesn't support uniform quantized types, then we would decompose this into different int types. And we have this pass called MHLO legalized to int pass, which will unpack the uniform quantized types into int. So it would look something like the following. So now you see that unlike the previous MLIR, now we have, for example, convolution has the inputs of I8 and outputting I32, etc., like that. So of course, it's a bit more verbose, but in int types. So that is what you would see for server side. And so now let me take you to ODML side. So for ODML, StableHLO quantizer is integrated into TF-Lite converter, as I said. And you can see that the API itself is pretty similar in that we still use the quantization configuration, which has all the information on how to quantize the model and what to do with the specific details. And we're just going to feed this information into the converter's flag called experimental StableHLO quantizer config. And if this is provided, then instead of running the usual TF-Lite quantizer, this is going to actually run the StableHLO quantizer. And so that's going to end up in the StableHLO quantized module that we previously also saw in server side. But of course, because we want this to also be viable for many TF-Lite files that ODML folks use, we also provide a legalization pass from quantized StableHLO ops into quantized TF-Lite. So in the end, you would have the option to write this as a quantized TF-Lite file as a flat buffer format. So let me show you the graph outputs. So the actual output of the quantization is going to be very similar to server side, as actually it's just going to be identical in this demo specifically. But of course, because ODML has a lot more constraints in terms of model size or latency or anything like that, it's going to want a bigger coverage in terms of op coverage for quantization and not just variants of denser convolution. So it's just going to look similar to what we had for server side in terms of quantized StableHLO graph, but much more up coverage. And so that's what we have. But we also, of course, as I said earlier, have legalization paths from quantized StableHLO into quantized TF-Lite. And that's going to be done by uniform quantized StableHLO to TF-Lite pass, which is going to do the legalizations, making the graph looking something like this. And one thing to note is that if you are using TF-Lite, then you can utilize the StableHLO quantizer by because you can still have the output of quantized TF-Lite. The StableHLO quantizer can give you the benefit of supporting multi-framework of JAX, PyTorch, etc., as Kevin mentioned. So that's one of the benefits of using it if you are already depending on TF-Lite files or ops. Yeah, so that was a very quick demonstration of the StableHLO APIs. And if you have any questions, we'd love to take them. Anyone from the GVCs as well? All right. All right. Yeah, I guess we're all hungry for lunch. Okay, so all right. So all right, then let's end earlier. And if you could please either look at the email for no before you go or this thing. Please let us know what you think so that we can improve the session to be more helpful for you. So yeah, thank you. And see you all after lunch and hope to see you in the lab sessions. Thank you.
So the morning tutorial survey link